Hello, everybody, and welcome to Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and today we're going to be talking about properties of energy. So this is kind of a start off to what this module is going to focus on, which is energy and how energy and heat function across our planet. So to start off, let's just think of Earth and say that Earth functions as a system of interconnected flows of energy and matter, because that's what it is. So energy simply is the ability or capacity to do work. Work is the energy transferred to or from an object via the application of force. Force is mass times the acceleration of an object. So basically, yeah, there's our three kind of broad definitions there of starting with energy. So energy is a measurable quantity, as we may recall from our intro definitions lecture. We have the calorie, which is the thermal energy required to raise the temperature of 1 gram of water 1 degree Celsius. We have the joule, or joules, is the energy expended by a force of 1 Newton acting over a distance of 1 meter. We can relate those two. 1 calorie is more or less equal to 4.19 joules. 1 joule is equal to more or less 0.239 calories. So we have two primary forms of energy, right? We've got kinetic energy, which includes the motions of waves, electrons, atoms, molecules, substances, and objects. We have potential energy, which is the stored energy in the energy of position. Within kinetic energy, we've got a few primary types. We've got radiant energy, which is the electromagnetic energy that travels in transverse waves. So radiant energy includes visible light, X-rays, gamma rays, and radio waves. Light is one type of radiant energy. Sunshine is also that radiant energy and provides fuel and warmth that make life on Earth possible. Thermal energy is the heat, thermal energy or heat is the energy that comes from the movement of atoms and molecules in a substance. Heat increases when these particles move faster. Geothermal energy is the thermal energy of the Earth. We've got mechanical energy. Mechanical energy is just the energy stored in objects by tension. So compressed springs and stretched rubber bands are examples of mechanical energy. And then hopping back over to potential energy, the one that we're most concerned or interested in is pressure energy. Pressure energy is the energy in or of a fluid due to the applied pressure as force per area. We have a fun relationship known as the Bernoulli principle, which drives pressure energy and relates it to potential energy, which we'll talk about in the next slide here. But pressure energy is one of those really important ones to what we're doing and what we care about in this class. Why? Well, it's the difference in pressure, or the pressure gradient force, that drives wind across the surface of our planet. And some of the bigger, broader atmospheric and meteorological systems that move across our world. So pressure energy is a really important one for us. Here is our Bernoulli principle, right? So often cited example of the Bernoulli equation is the reduction in pressure, which occurs when the fluid speed increases. So at V1, our fluid is flowing through a broader pipe. The flow velocity has to increase to move the exact same amount through so that it equals the pressure on either side. So if we look at that equation up top, energy per unit volume before equals energy per unit volume after. Pressure 1, or pressure energy, plus kinetic energy per unit volume plus the potential energy per unit volume is going to equal the same thing on the other side of the equation. So what you see is an increase in fluid speed when your pressure is increased. You have a smaller pipe, for example, and you have a decrease in internal pressure. So Bernoulli is not something we're going to dive into, so just don't worry. It's just something I wanted to mention and talk about a little bit, but it is not something that you need to know for this course. So don't worry about that. Worry about that if you're taking a physics course. Now we're going to actually get into some energy laws, ones that we do care about. nothing against Bernoulli, but the first one is the first law of thermodynamics. First law of thermodynamics is just the application of the conservation of energy principle to heat and thermodynamic processes. It says that the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. What it really comes down to is energy in is going to equal energy out in some way, shape, or form, whether that's waste energy or just pure energy that's being converted from one form to another. Now, the second law of thermodynamics says that energy always flows spontaneously away from being concentrated in one place, becoming dispersed and spread out unless something keeps it from doing so. What's a great example of this? A nice casserole, which on a nice winter day like today, that looks pretty good. A nice ham and cheese casserole sounds really good right about now. But what we're seeing here, notice that some areas, for whatever reason, are nice, this nice yellow, creamy, cheesy color, while others are browner, and you see those more crispier, when you say caramelized bits, that aren't ubiquitous across the surface. Well, heat is flowing spontaneously away from this. So some areas, like the tips of the ham or some portions of the cheese, are browning because they are cooking, there's more heat flowing through them than other portions of the casserole. So just kind of a good Midwestern way to show kind of the second law of thermodynamics. A corollary to that second law says that thermal energy always flows spontaneously from warmer to colder areas unless something keeps it from doing so. So let's look at the mechanisms of energy transfer here. Start off, we've got a pot that is on an electric coil heating element and is full of water. The first one, conduction, transfers heat via direct molecular collision. An area with greater kinetic energy will transfer thermal energy to an area with lower kinetic energy. Higher speed particles will collide with slower speed particles. The slower speed particles will increase in kinetic energy as a result. Conduction is the most common form of heat transfer and occurs from physical contact. Here, that very hot electric coil has a much higher energy that is being transferred to the bottom of the pot. And the bottom of the pot is then transferring it to the water. So convection, when a fluid such as air or liquid is heated and then travels away from the source, it carries thermal energy along with it. This type of heat transfer is called convection. The fluid above a hot surface expands, becomes less dense, and rises. Hot air rises. Hot fluid rises. We know this. So you have conduction, which is the physical heating of the bottom of the pan, which is then heating the water. Once the water heats enough and turns to steam, convects away, or that hot air is moving away from an area of less dense to more dense. It's trying to equilibrate that pressure gradient. And then we've got thermal radiation, which is basically generates from the emission of electromagnetic waves. You don't see this one. It's not the coil, and it's not, visible as something like steam. It's the heat radiating off of that pan. You can put your hand, if this was the pan and my hand was about an inch away from the edge of that pan, it's still going to feel really hot, right? Because energy is radiating away from that surface. So these waves carry energy away from the emitting object. Radiation occurs through a vacuum or any transparent medium, either solid or fluid. Thermal radiation is the direct result of random movements of atoms and molecules in a matter. Movement of charged protons and electrons results in the emission of electromagnetic radiation. But all of this we're seeing here is a form of radiant energy. What is the primary source of, say, radiant energy to our planet? Any guesses? The sun, aka solar energy. So obviously our sun is quite far away from us, 150 million kilometers, but it is emitting incredible amounts of energy through nuclear fission and reaction within the core and across the body of the sun. So that's where we get all of our energy. We ask ourselves, what is radiant energy? We kind of talked about it, but radiant energy is just one of the many forms or types of energy throughout our world. It's a stream of particles of pure energy, like photons, or a stream of waves of pure energy, like electromagnetic waves. We call, for example, the waves the electromagnetic radiation, or EMR. There's a few things we care about when it comes to electromagnetic radiation. First off, it can pass through a vacuum. Very important because space is a vacuum. It travels at the speed of light through that vacuum, which again, really important when the sun is your primary emitter. And it is emitted by all matter. Warmer matter emits more electromagnetic radiation per unit area than colder matter does. And warmer matter emits electromagnetic radiation with shorter wavelengths, while colder matter emits electromagnetic radiation with longer wavelengths. Here we can see these alternating sources of mechanical and electric energy. We have a wavelength here, and basically these alternating sources of magnetic and electric energy are propelling this wave forward. So the range of possible electromagnetic wavelengths is called, anybody? Electromagnetic spectrum. Here it is in all of its glory. We can see a few things just for understanding what we're looking at here. Our wavelength, note, is in micrometers. Higher energy, shorter wavelength, higher frequency waves are on the left-hand side, our gamma rays, our X-rays, our ultraviolet rays. Our lower energy, longer wavelength, lower frequency is on the right-hand side, our radio waves, our microwaves, our infrared waves. You can see our ultraviolet here. Those are some of the ones that are really important to us coming into the planet, right? Visible light also is incredibly important to us. That's what our eyes see. Near infrared, thermal infrared, and far infrared are also very important to things like plant life. What our planet is emitting thermal infrared radiation. See, UVC functions at about 100 to 200 nanometers is the band length. I'm sorry, I said micrometers, I meant nanometers. UVB functions at about 280 to 315 nanometers. UVA functions at about 315 to 400 nanometers. Near infrared, about 0.7 to 4 micrometers. Thermal infrared from about 4 to 100 micrometers. So what happens then when electromagnetic energy or radiation strikes matter? Well, it can be absorbed, redirected, unaffected, it can just pass through. So if we're looking at the energy coming into our planet from the sun, which is about 5,500 degrees Celsius at its surface, emitting in all directions, that's a pretty substantial amount of energy coming in. So we've got 3.83 times 10 to the 26th watts of energy that are being emitted from the sun here, for example. 1 watt is equal to 1 joule per second. About 7% of that is ultraviolet radiation. About 46.5% comes in the visible radiation form, or visible light spectrum. And then about 46.5 is in the near infrared spectrum. Earth encounters about 1.74 times 10 to the 17th watts of energy, kind of cumulatively, in the form of what we call incoming solar radiation, or insolation for short. So if we look at Earth, we can assume that basically the rays of light, example, these arrows here, these yellow arrows, are coming to Earth, and we assume, because they really are basically parallel fashion. So we've got 1.74 times 10 to the 17th watts coming into our planet. We radiate 100% thermal energy. So if we've got 1.74 times 10 to the 17th watts coming in, how many do we have going out as thermal energy? Well, if we think of those laws of thermodynamics that we talked about, energy in means or equals energy out. You have to have a balance. So it's 1.74 times 10 to the 17th watts going out. We call that thermodynamic equilibrium. So that's very important when you look at balancing energy. So more energy coming in means that it's going to be warmer, but more energy has to go out. So the energy coming in is met and balanced by the energy going out of our system. So if, for example, there was less solar activity, there would be less output. There was more solar activity, there would be more output, etc. Electromagnetic radiation laws are the next thing we're going to talk about. The first law, the Law 1, emission of radiation. All substances emit radiation as long as their temperature is above absolute zero, so 0 Kelvin, or negative 273 degrees Celsius. Law number 2, Blackbody and Planck function concept, says that the sun is very similar to an ideal emitter, or blackbody. Blackbody is a hypothetical object that absorbs all of the radiation that strikes it. It also emits radiation at a maximum rate for its given temperature. Blackbodies exhibit a defined relationship between the intensity of radiation energy, or the amount of radiation flux they give off, and the wavelength of that radiation. This relationship is what we call the Planck function. So Planck's law, simplified, we can see here. So, pardon me. In 1900, Max Planck postulated that electromagnetic energy is emitted by discrete portions, or quants, rather than continuously. Light can be considered not only as a wave-like entity, but also as a particle or photon with the energy given by Planck's law. An easy way to remember the blackbody and Planck function concepts are that the shorter the wavelength, the greater the intensity of the energy flux. So if you're trying to figure it out, E, or energy, is equal to hc over lambda. H is Planck's constant, c is the speed of light, lambda is your wavelength. Law 3, the Stefan Boltzmann law, says the total amount of radiation given off is proportional to the fourth power of its absolute temperature. Or the emission rate of electromagnetic energy is directly related to the temperature of the matter emitting it. We see here I equals spacing space sigma. Sorry, it's been a while. I is equal to sigma times T to the fourth, or temperature. So in this case, I is actually epsilon. It's our electromagnetic radiation emission rate, or watts per meter squared. T is our temperature in Kelvin to the fourth power. So just a quick 0 degrees Celsius is equal to 273.15 degrees Kelvin. 100 degrees Celsius is equal to 373.15 degrees Kelvin. Sigma is our Stefan Boltzmann constant, or 5.67 times 10 to the negative eighth watts per Kelvin meter squared. So basically what this law does is that it links the total amount of energy flux that's emitted by a black body to the body's temperature, or fourth power of the body's absolute temperature, if we're splitting hairs here. The hotter the body, the much greater, it's to the fourth power, the much greater the amount of energy flux or radiation. This concept is important, though, because it means that the amount of radiation given off by a body is a very sensitive function of its temperature. Small changes in temperature can lead to big changes in the amount of radiation given off. Although, proviso, it only pertains to black bodies. We're assuming, because it only applies to black bodies, that emissivity, or epsilon, is kind of negligible, we'll say. We're assuming it's 1. It equals 1. This is from 0 to 1 is what this epsilon would be. We're assuming it's 1. So, negligible. Electromagnetic radiation law number 4, temperature and wavelength. As substances get hotter, the wavelength at which radiation is emitted will become shorter. This is also what we call Wien's displacement law, which basically just says that the wavelength of maximum electromagnetic radiation is displaced to shorter values as the temperature of matter increases. It looks like this. Lambda max equals B over T. So lambda max is the wavelength in the spectrum at which the energy peak occurs. B is Wien's displacement constant, which equals 2,898 micrometers Kelvin. And T is the absolute temperature of that body in Kelvin. Basically, what we're saying here is that the hotter the body, the shorter the wavelength, and the cooler the body, the longer the wavelength. Pretty simple. This is an important concept because it means that objects, super hot objects like the sun, that radiate like black bodies are going to radiate the maximum amount of energy at shorter wavelengths, whereas cooler bodies will radiate most of their energy at longer wavelengths. In our world, literally, the sun is that very hot body. We, Earth, the planet, is that cooler body that's emitting at so instead of things like UV, ultraviolet radiation, visible light, and infrared radiation, we emit energy at thermal infrared. So kind of that middling infrared, longer wavelength energy spectrum. So we give out a longer wavelength than we take in, for example. So just as a quick recap, we talked about what energy is, first and second laws of thermodynamics, emission of radiation, the blackbody and Planck function concepts, the Stefan-Boltzmann law, and Wien's displacement law. So that's it for this one. There's a couple more to come in this week, or this module. It's a little bit chunkier of a module just because there's a lot of things we want to get through. And the start of the class so that we can really focus on weather interpretation. But first, we got to understand how to get there and how energy fluctuates across our planet. If we know that, we understand heat distribution across our planet, which then drives pressure gradient forces and winds, et cetera, et cetera, et cetera. So this is where we're starting. We'll get to the fun stuff here soon enough. So hope you enjoyed this one, and we will see you in the next video.